Welcome to Easy BTech, your guide for BTech and beyond. Today learn about the performance of medium transmission lines. So, medium transmission lines. Okay, in medium transmission line, we have to consider the effect of capacitance. We have to consider the effect of shunt capacitance in transmission line. Here question is where we have to consider the capacitance in the line. Okay, now we will take the transmission line. Okay, here I am taking the effect of capacitance. Assume that it is a three cases, case 1, case 2, case 3. The three cases, it is a medium transmission line. Here question is where we consider the effect of capacitance. Sending end, this is the receiving end. Sending end, the receiving end. Sending end, receiving. Now, where we have to consider the capacitance. In first case, we will consider the capacitance at near to the load. Okay, in this case is called load end condenser method. Condenser is nothing but the capacitance. It is near to the load, then it is called load end condenser method. This is one assumption. Another assumption is the capacitance is exact at midpoint of the transmission line. This is it is look like a T. That's why it is called nominal T method. And in another method we will take the capacitance of the capacitance at sending end, of the capacitance at the receiving end. This is another assumption. It is look like a nominal, it is look like a pi, that's why it is called nominal pi method. Nominal pi method. Actually it is a distributive parameter. For our convenience, for simplification of calculations, we are taking below 160, the capacitance, resistance, inductance are lumped parameters. In the lumped parameters, where we have to connect the capacitance, that is the task. Okay, that's why we are assuming the entire capacitance is at near to the load center, midpoint of the transmission line, of the capacitance of sending end, of the capacitance at receiving end. Okay, now first we will see the load end condenser method. Case 1, load end condenser method. In load end condenser method, the capacitance is at near to the receiving end. Okay, this is sending end Vs. Here we have the load. Is load. Near to the load we have a capacitor. Okay, and the resistance, and this is inductance, okay, or XL. The current flowing through the load or receiving end is IR. The current flowing through the capacitance is IC. The current flowing through the transmission line is IS. Throughout this point, up to this point it is IS. Okay, it is divided into IC and IR. Okay. here I want to draw the phasor diagram for this case. In phasor diagram, I am taking VR is the reference. Okay, VR is the reference, and the current IR lagging with the VS at an angle of phi r. Is phi r. It is the current here. It is the reference vector VR. Okay. Now here observe the diagram. Is equals to sum of, apply KCL here. Is equals to IC plus IR. From this diagram, it is Is equals to IR plus IC. Okay. IC across the voltage is VR, therefore it leads the VR with 90 degrees. Therefore, I am taking the IC. IC leads the VR at an angle of 90. This is IC. Therefore, in the vector diagram, the addition of this vector sum of these two it is IC. Therefore, IR plus IC you get this is Is. The current flowing through the resistance R is Is. Therefore, the Is into R drop is in phase with the Is vector. It is Is into R drop, and Is, the current flowing through the XL is also Is. Therefore, is I into XL drop is perpendicular to I into R drop. It is Is into R drop. It is Is into XL drop. Therefore, sum of this drops is Vs. This is Vs. It is Vs. Okay. If you know the impedance, then it is Is into Z. Is vector into Z. Okay, this is the phasor diagram for load and condenser method. From that, we will derive the expressions for sending end current and sending end voltage. First, I calculate sending end current. Before going to that, I have to what are the parameters is there in the medium transmission line. First, we have the resistance in ohms per phase. XL is a reactance ohm per phase, and C is capacitance taking the XC is capacitance per phase. In some cases, they are giving admittance move per phase. Vs is sending end voltage. Vr is receiving end voltage. Is is sending end current. All the parameters are per phase. IR is receiving end current. And cos pi r is power factor of a receiving end. cos pi s is power factor of sending end. Those are the parameters we have for medium transmission line load end condenser method. Okay, now I will take the apply KCL here. Apply KCL here. The IS equals to IC plus IR. So we have to take the current. IS vector equals to IR vector plus IC vector. Okay. Now here VR vector equals to VR plus J0 because I am taking reference is VR vector. IR vector equals to magnitude of receiving end current into cos pi r minus J sin phi r for lagging power factor. IC vector equals to, it is the voltage across the capacitor is VR, therefore it is J omega C VR vector. If the given admittance, then it is J V or vector into Y vector. Okay. Now, if you add these two terms, substitute IC and IR in equation, this equation, IS equation, we get IS vector equals to IR vector plus IC vector. Therefore, it is IR plus VRY. Okay. Now, you can calculate the VS vector. VS vector equals to VR vector plus the current flowing through the transmission line is IS, the impedance is Z, where Z vector equals to R plus J XL. Okay. If you substitute the values here, it is VR plus J0 into plus IS into vector. We calculated IS here, okay, from equation 2, R equals to R plus J XL. Okay. Now for VS vector, if you calculate ABCD parameters, for calculating ABCD parameters, VS equals to VR plus IS we represent with IR plus VRY into Z. It is VR plus I into R plus IR into Z plus VR into Y into Z. If you common VR from these two terms, it becomes VR into 1 plus YZ plus VR into Z VS. This is equation 3. This is equation 2. Compare equation 2 and 3, we will get the ABCD parameters of load and condenser method. We know that Vs equals to AVR minus BIR, IS equals to CVR minus DIR. Therefore, from this one, this is A, this is B. Therefore, ABCD parameters of load and condenser method is A equals to 1 plus YZ, B equals to Z, and from IS what you get, IS equals to IR plus VR into Z. Therefore, C VR into Y, sorry, this is VR into Y, therefore C equals to Y and A equals to 1. This is the ABCD parameters for load and condenser method. Okay. Now, after calculating Vs and Is, we can calculate the efficiency of transmission line. It is output by output plus losses into 100. The losses are for single phase. If transmission line is a single phase, the losses are I square into R. If the transmission line is three phase, it is 3I square into R. Now, regulation, percentage regulation, we know the formula. V no load minus V full load divided by V full load into 100. Now, what is V no load? V no load is nothing but there is no current, load current, it is IR equals to 0. If IR equals to 0, the receiving end voltage is, I will draw the diagram. This is resistance, this is inductance, this is capacitance. IR equals to 0, it is open circuited. Therefore, receiving end voltage is nothing but the voltage across the capacitance. Okay, we can take it is Y, it is XL, it is R, it is Vs. Okay, it is voltage division rule. I think you know the voltage division rule. The voltage division rule is nothing but it is Z1 and Z2, both are connected in series, Vs. Therefore, the voltage across Z2, the voltage across Z2 equals to source voltage into Z1, sorry, same impedance. What is the impedance? Where we have to find Vs into Z2 divided by Z1 plus Z2. This is the expression. Therefore, I am taking it is Z1, I am taking it is Z2. Therefore, VNL at no load equals to Vs into minus J by Y divided by Z1 is R plus JXL, Z2 is minus J by Y. If the given capacitance, therefore, replace this Y with omega C in problems. Okay, the formula becomes Vs into minus J by omega C divided by R plus JXL minus J by omega C. Okay, this is the way we will calculate the no load voltage. After calculating the no load voltage, we will get the regulation. The percentage regulation equals to V no load minus V full load divided by V full load into 100. If the given ABCD parameters, we know Vs equals to AVR minus BIR. From this equation, IR equals to 0 for no load condition. Therefore, VR at no load equals to Vs by A also, if you know the term A. Okay, you can use this one also for calculating this no load voltage. Okay, this is the way we will calculate the regulation, efficiency, sending end voltage, sending end current in medium transmission line under load and condenser method. Now we will see the problem on this load and condenser method. Okay, problem is they will provide a single phase transmission line has 100 kilometers long, as the resistance is 0.4 ohm, and inductance is 0.6 ohm, and inductive admittance is 14 micro ohm, and the receiving end voltage is 33 kV. The power factor at the receiving end is 0.8 power factor lagging. They mention, assume the capacitance, the total capacitance. The total capacitance is located at receiving end. Means it is nothing but load and condenser method. Okay, load and condenser method. What here we have to find? Here we have to find sending end voltage, sending end current, sending end power factor, percentage regulation, and efficiency of this transmission line. First, it is all the values in kilometers. So they given for kilometer. The resistance, inductance, and capacitances are per kilometer. Okay, here first of all we have to calculate the resistance and inductance and admittance for 100 kilometers. Therefore, first calculate the resistance of the transmission line 0.4 into 100. Again get 40 ohm. XL equals to 0.6 into 100. You get 60 ohm. Admittance equals to 14 micro, 10 power minus 6 into 100. You get 14 into 10 power minus 4 Siemens. Okay. Now, the given VR is 33 kV, means it is 33,000. It is a single phase, so I no need to convert per phase. Already it is in per phase. Now, for calculating IS, the given, sorry, here I mentioned the load is 5 megawatt. The given load is 5 megawatt. Therefore, I will calculate the current I equals to I, or receiving end current equals to P by V cos pi R for single phase. Therefore, it is 5 megawatt for 5 into 10 power 6. V is 33,000 into 0.8. I will get the current equals to 189.4 amperes. Okay, now after calculating IR, I have to calculate IR vector. IR vector equals to IR into cos pi R minus J sin pi R. IR value is 189.4, 0.8 minus J 0.6. Sin pi R is sin of cos inverse 0.8, you get 0.6. Okay, or in polar form it is 189.4 at an angle minus 36.86 amperes. Okay, now, and I have to calculate z vector equals to R plus JXL. It is 40 plus J60. In polar form it is 72.11 at an angle 56.31 ohm. Now I will calculate IC vector equals to JVR into Y. Okay, it is VR is 33,000 and Y equals to 14 into 10 power minus 4. The current is 46.2 amperes. Now IS equals to, from the load and condenser method, IS equals to R vector plus IC vector. IR vector is 189.4 at an angle minus 36.6. We can write this in polar form, 46.2 at an angle 90. Okay? Therefore, plus 46.2 at an angle 90. You get the current is 151.52 minus J 37.44. To convert this one into polar, you get 165.85 at an angle minus 24 amperes. Okay, this is IS. Next, VS equals to VS vector equals to VR vector plus IS vector into Z vector. VR vector is 33,000 plus J0 plus IS vector is 165.85 at an angle minus 24 into Z is 72.11 at an angle 56.31. After multiplying this, you get VS equals to 43107.74 plus J 6392.32. Convert this one into polar form, you get 43579.11 at an angle 8.43 volts. Therefore, if you observe the phasor diagram, in the phasor diagram it is VS, sorry, it is VR, it is VS, it is IR add with the IC, you can get IS. Here the angle between VR and IR is phi R. The angle between VS and IS is phi S. At IS calculation, you get IS is at an angle 24. Means with reference to the receiving end, the angle is 24. VS at an angle 8.43. It is the angle between VS and VR. Therefore, the angle between VS and IS is the sum of 8.24 plus 24. Therefore, power factor of sending end is cos of, the power factor of sending is cos of 8.24 plus 24. You get cos pi s equals to 0.844. Now, we will go the calculations of efficiency. Efficiency is output by input. Output is VR, IR, cos pi r. Input is VS, IS, cos pi s, 200. All the terms you know, no need to go for output by output plus losses. If you want, you can go through that. Here all the terms is there. That's why I am calculating efficiency directly from this formula. 33,000 into, I am taking only magnitudes, 189.4 into 0.8 divided by the sending end voltage is 43579.1. The sending end current is 165.85 into the power factor is 0.844 into 100. Again, the efficiency is 81.96%. Like that, I have to calculate for regulation. For regulation calculation, we know that percentage regulation equals to V no load minus V full load divided by V full load into 100. Here V full load is 33,000. V no load equals to, we know the formula V no load equals to Vs into minus J by Y divided by R plus JXL minus J by Y. Okay. Substitute all the values here. Vs equals to 43579.11 minus j by 14 into 10 power minus 4 divided by R is 40 plus j60 minus j by 14 into 10 power minus 4. Get the no load voltage. The no load voltage equals to 47485.86 at an angle minus 3.5 volts. I take magnitude only for this calculation. Therefore, percentage regulation equals to the no load voltage is 47485.86 minus the load voltage is 33,000 divided by 33,000 into 100. You get the regulation is 43.9%. Okay. From this load and condenser method, what you observe is the drawbacks of this load and condenser method is actually the capacitance is not completely concentrated at the load end. Okay, it is the wrong analysis. That by here we are having some errors in the calculations. In the results, we are having some errors in the results. Okay, it is the not exact method for considering the capacitance at the load end. That's why that is not correct analysis. Okay, correct assumption. Second one is it overestimate the results. It is overestimate the results. So that are the drawbacks of load and condenser method. Okay. For avoiding this one, we will go for a nominal T method. With better assumption, we will go for the nominal pi method. Okay. Thank you very much.